Yo, I'm live. That's crazy. That's crazy. Is that what? I don't know. I know my thumbnail game is terrible. Just. Oh, there's 2 people watching. Who's watching? Can people say something in the chat so I know who's watching? I'm just curious. No one? All right. It's unfortunate. Okay. I'm just pulling up the relevant documents. Okay. 3 people. Oh my god. Can people say something in the chat? This is just so I know you're there. I'm curious who these 3 people are. Can you not edit the chat or something? I have no idea. If anyone has my number, just text me. If that's not possible. Oh, I can look at the participants. It just says me. We'll start in a couple minutes. I'll wait a couple minutes. If people are going to join. This is weird, but cool. Thank you. I know my thumbnail game is terrible. That thumbnail was not great, but I'm not stressing about that. Oh, there's only 1 participant. Okay. I'll wait until 3:33, and then we can start. Okay. Appears. All right. I don't know my water. Oh, 3 participants. This is crazy. Okay. Okay. All right. Let's begin. So, make sure my camera's ready. All right. So, 2019 B3. This is a very difficult problem. In fact, it was actually one of the hardest on the exam. Among the B section, it should have been B5. It should have been the 5th problem out of 6, but it was placed as the 3rd problem. When I solved it, I made some important developments, but I didn't solve it all the way. I got maybe like halfway there or something like that. And when I reviewed it, most of the solutions were very algebraic and were like going completely over my head because a lot of them just used a lot of complex manipulations that I would never be able to make up on the test. But there was one solution which is very nice and which was more in line with what I was actually going for. So my dog is saying hi, sir. In case you guys want to see my dog, she's saying hi. Okay. Anyway, there's one solution which was a lot more in line with what I was going for, and it's actually quite nice. I mean, still kind of hard, but it's quite nice. And this is the one that I'm going to present to you. So first, we're going to talk about, I guess I haven't introduced the problem. I will do that after I discuss something that will become very relevant. So, so first I'm going to talk about, is someone in the, sorry, Brouwer's fixed point theorem. Okay. So the kind of formal statement of this is that any continuous function mapping a compact convex set to itself has a fixed point. Now, what does that mean, like intuitively? What it means is that, so for example, let's say you have a disk. Okay, that was terrible, but you get the idea. Let's say you have a disk, and you take every point in the disk and you map it to some other point on sort of like within the same disk. Okay. So, and you map it continuously from here to here. What Brouwer's fixed point theorem says is that there's at least one point in the disk which maps to itself. You can't map all the points to different points. Okay. If I use a good way to explain this kind of like in layman's terms, I guess, is, let me write it out. So Brouwer's fixed point theorem. Okay. So if you have like if you take a cup of coffee, for example, sorry, the glare is really bad. I'll just have to deal with that. But yeah, my camera is also pretty bad, but I will try and write big enough so you guys can read that. So a good example would be, if you, for example, if you have for like a cup of coffee and you stir the cup of coffee, then no matter how much you stir it, there's always going to be one point like in the coffee which will stir back to itself, no matter how hard you try or how much you try to mix it up, right? So that's the general idea. And the most important condition that you want to focus on is the fact that the set has to be convex. Okay, compactness is something that's usually don't have to worry about too much. The convex part is like the part that it is more likely to violate the condition. So, for example, if you have a washer where there's a hole in the middle, right? And you have all these points. It's like a donut. If you just rotate all these points, right? If you just rotate them, then no point will map to itself, right? So the theorem doesn't apply because it's not convex. Of course, if you had a disk and you did the same rotation, if you had a disk and you did the same rotation, the center point would map to itself. So it applies in that case. Okay. So I'm going to try and explain kind of the proof or the idea for why this is the case. It's a very this is a pretty advanced theory. So I'm going to try to explain as best as I can and give the main idea. Now, first, and this is a good general strategy, is that we're going to start in one dimension and we're going to prove it in one dimension and try to go up. So in one dimension, we're going to imagine mapping the interval actually, let me 0 to 1. So we're going to take the points in 0 to 1, and we're going to map them to, or I will I'll write it under. And we're going to map them to the same interval. And what we want to show is that at least one of these points, and again, this function is continuous. Okay. What we want to show is at least one of these points will go directly down. Like it will go, it will map to itself. Now, what we can do is think about, we can define, so let's say the function is f. We can define a function g of x, which is equal to f of x, g of 0, right? 0 is going to map to some point, which is like 0.3, 0.5, 0.2. But the main idea is that 0 will map to a point which has an x value greater than it. Or it will map directly to 0, in which case we've proven it, right? Because 0 will be 0 minus 0. On the flip side, right, f of 1 will always be less than or equal to 1, right? Because, I mean, it has to be. So what that means is that g of 1, f of 1 minus 1, will be less than or equal to 0. And so if g of 0 is greater than or equal to 0, and g of 1 is less than or equal to 0, then by the intermediate value theorem, there's a point in this interval for which g of x will equal 0, and that one f of x equals x. You can imagine drawing word as well. 0 is going to the right, left. So if you imagine drawing all these arrows, and it's a continuous function, right? There must be a point at which this arrow kind of flips, and when it's going straight down, right? And that will be where your fixed point is. Okay, one-dimensional case, just intermediate value theorem. Pretty straightforward, but not, I mean, I wouldn't say trivial. It's still a bit difficult. Okay, now in 2 dimensions, we're going to look at the unit square. This is where it gets a little bit harder, but this is where a lot of the big ideas come through. So we're going to map every point in the unit square to another point in the unit square. Okay, and I claim that there's one point in the unit square that will map to itself. Okay, or at least 1 point. Okay. Now the key here is to think in, okay, yeah, the corner that says 0 up in the corner. Not super important. The key here is to think in 1 dimension, right? So what we want to do is, if we look at this bottom edge here, 0 to 1, right? And we think about only the x-coordinate of the image, okay? So the x-coordinate of the image of 0 will be, inward, right? Inward sum. And the x-coordinate of the image of 1 will be inward sum as well. Basically, the point I'm trying to make is that if you think only about the x-coordinate and you look at just this bottom edge here and where what the x-coordinates map to, by the one-dimensional case, there must be a point within this bottom edge where that point will map to a point with the same x-coordinate, right? Don't know how well I explained that, but basically, if you just think about one coordinate and you just look at one edge, then there's going to be, it's the one-dimensional case, right? Now, similarly, if you imagine continuously going up, along these 2 edges, right? Between any 2 of these points on the boundary, we can make the same argument and find another point whose x-coordinate will be the same, right? Will map to itself. And that will happen continuously. So the result is that inside the square, connecting between these 2 edges, you get some kind of curve where within the curve, wait 1 sec, let me check. Yeah, so you get some kind of curve where within the curve, the x-coordinate along this curve, every point along this curve, it will map to a point with the same x-coordinate, right? So that will be invariant. Is my camera backwards for you guys? Can someone if someone's watching who has can text me? Is my camera backwards? Because it looks backwards on my screen. It's fine. Okay, cool. All right. So now what we do is we make the same argument, but with y coordinates. So what we say is between these two, I guess this is kind of confusing, but between these two vertices here, right, there must be a point. If we just think about where the y coordinates map, there must be a point along this edge where that point maps to a point with the same y coordinate, right? Just reduces to the one-dimensional case because we're just thinking about one dimension in general, right? And then we make the same argument and we say there must be some curve which connect from this edge to this edge, where every point along this curve, the y coordinate of its image will be the same, right? And so what that means is along this curve, point will map to the same x coordinate, right? And along this curve, point will map to the same y coordinate. So at the intersection of these two curves is a point which maps to both same x coordinate and same y coordinate, and it's a fixed point, right? Okay, that one's obviously a harder case to deal with, the two-dimensional case, but that's the main idea. Okay, now I'm going to talk lastly about the unit cube. Okay, so we're going to go to 3 dimensions, but it's actually going to be a lot of the same ideas as the two-dimensional case. Okay, so now for 3 dimensions, looking at the unit cube. And so we'll say this is x, and then this is y, and this is z. I think you guys can kind of see that. Okay. Now, what we do is say, we do the same argument, okay, but we look between 2 faces now. So if we look at this face, which is back here, right, and this face over here, these 2 opposite faces, and we think about just the x coordinate, right? Actually, first let's start with just this bottom edge, okay? This bottom edge here, and we think only in terms of the x coordinates. There's a point along this bottom edge where, that point maps to a point with the same x coordinate. And then if we, in general, if we take any 2 opposite points, right, any 2 points on these opposite edges here, then, which are like directly across, then within, like between those 2 points on that line, there must be a point which maps to the same x coordinate, right? Because along this face, x is 0, along this face, x is 1. So by the one-dimensional argument, right, there must be a point in between, which is fixed in x. Okay. Now, if we think about that, so we think about any set of 2 points on these 2 faces, which are directly across from each other, it's going to produce a point in the middle where it's fixed in x. So you get this kind of like plane thing, which goes through the cube. It's not really a plane, but it's like a, I don't know, planar curve. I don't know if that's the right terminology, but some kind of curve which cuts through the cube, right? Not parallel, but in between those 2 opposite faces, right? And along this curve, every point along this curve will map to a point with the same x coordinate. Then we do the same thing for y and for z, and we get 2 more of these curve things, okay? These or plane things. And at the intersection of the 3 of them, there's a point which both maps to the same x coordinate, same y coordinate, and same z coordinate, and so it's a fixed point. Okay, so that's in 3 dimensions, right? That's the 3-dimensional case. And so in general, you can imagine if you generalize this to any dimension, the same argument is going to kind of apply, right? Because you kind of have like the intersection of, in 4 dimensions, you have the intersection of 4 like hyperplanes or cubes or something like that, and it would intersect at a point. And so we could morph the cube into any 3-dimensional sort of object which is convex continuously, and the same argument would apply, right? Because we can kind of morph it back, and there must still be a fixed point. I know it's really hand wavy, but let's go to the problem. So I'm pulling it up right now. Oh wow, we have 4. Okay, cool. Oh, now 2. It's sad. All right. So now the actual problem. I posted it in the group. I'm not going to write it down. I'll just read it out. So you have, so let Q be an n by n real orthogonal matrix, and let U, actually I will write it out a little bit. So Q is an n by n real orthogonal matrix. And then U is a vector, which is, it's a vector in Rn that is, it's a unit vector in Rn. Okay, unit column vector. And P is equal to I minus 2 U transpose. And you want to show that if one, what is it? You want to show that if 1 is not an eigenvalue of Q, then 1 is an eigenvalue of PQ. Okay. So at least when I first looked at this problem, I thought it was very convoluted, right? I think it definitely comes off that way, as sort of like a bizarre, like the condition seems bizarre. If 1 is not an eigenvalue of Q, then 1 is an eigenvalue of PQ. And also just the setup just seems kind of out of left field. That was my initial thought. And so whenever you have like a linear algebra problem that you don't really have like a very good intuitive grasp on it at all, it could be good to think about it geometrically, and that's what I went for here. So what kind of made me think about this geometrically was a couple things. So for example, Q is an n by n real orthogonal matrix. Now geometrically, an orthogonal matrix, so I assume, like I said, you need to take linear algebra for this, but orthogonal matrix is a matrix whose column vectors are they're all unit vectors and they're all orthogonal to each other, right? They're orthonormal. And so geometrically, that represents just a rotation in space. So for example, like the rotation matrix that you learn when you kind of depends when you learn it, but when you first learn matrices, you sometimes learn the rotation matrix in 2 dimensions, which is like cosine theta minus sine theta, cosine theta, I think. I don't exactly remember. But that's an orthogonal matrix, and it represents a rotation in 2D space because all it does is rotate. And so that's relatively easy to visualize. So when I saw that Q was an n by n real orthogonal matrix, I was thinking, okay, I should try to visualize this, because just trying to do math with that is like doesn't seem as beneficial, right? Just doing algebra. So, oh yeah, I need to pull up how I explain this solution. And also, U being a unit vector, also very nice to visualize. So I just thought like going geometrically here, because going geometrically would help me understand what's going on. And lastly, what made me want to go geometric is the condition has to do with an eigenvalue of 1, right? Which has to do, like, if a matrix has an eigenvalue of 1, then there must be a fixed point, right, of the transformation, because that vector will map to itself. So that's why I started talking about Breyer's fixed point theorem. But that's also very like nice to visualize. Okay, so because we're going geometric, really the only thing we don't get geometrically is P. Okay, P seems like we don't have a good geometric understanding of that. So now, of course, we know what I does geometrically. Okay, it's just the identity, right? It does nothing. But really what we don't know is what this UU transpose is doing, right? That's the confusing part. Now, oh yeah, so So at least the geometric big idea that we're trying to prove is that you have basically, you say, so if Q doesn't have any fixed points, okay, so if Q just rotates every vector off of itself somehow, okay, then when we apply Q and then we apply P, right, PQ, that must have a fixed point. Okay, so that's the idea that we're trying to go for. So really what we care about is sort of like, we don't necessarily care specifically about P. We care about how P acts on some vector V, right? Because we want to show that, we care about, well, I guess it's sort of two different ways you could look at it. Like, you could either try to just figure out the matrix, or you could try to figure out how the matrix acts on a vector. And in that case, like, if you look at PV, that's actually more useful if you consider both of them. And the reason is, if you consider what PV equals, so, I guess I'm not doing this anymore. So PV equals I minus 2U U transpose V. And that equals, obviously I. It's just V minus 2U U transpose V. And the key thing to notice is this term here, and specifically this U transpose V. Because because you use a unit vector, that's just a dot product, right? That's the projection of V onto the direction of U, right? So let's think about this. Let's think about what U transpose V is doing, okay? So U transpose V will give you the scalar projection of what happens when you project V onto the direction of U. And then when we multiply by U, we get the vector version, right? So if we subtract U transpose V, right, from V, then that will give you, so U transpose V is giving you the vector projection. And so you have like V, and then you have the direction U, and what you get is the decomposition. I will draw that out because that was a bit, yeah, I will draw that out. So what we have is, let's say, okay. So let me, no, I think that's fine. So let's say this is the direction U of U. And we're looking in 2 dimensions, but we'll generalize in a moment. And so this is vector V. Then U transpose V gives you the scalar projection of V onto U. Right? So this bit. And then we multiply by the vector U, we actually get the vector version, right? So I'll call the, I'll say V equals D plus P. So P is the projection onto U, right? P is the projection onto U, and D is the decomposition. Okay. So V minus, so this is equal to V minus 2P, right? So P acting on V, and we'll call W equal to P acting on V. And that's going to be equal to, so that's equal to V minus, and then 2P. Now, what's also important to notice is that, well, if we take V and we subtract out the projection, that's just D. And then we're subtracting out another P. So actually, we get W is equal to D minus P. Okay, just a bunch of projection stuff. Sort of good amount of algebra, I guess. So let's draw this out. Let's draw out W. So this is V. This is like the line which corresponds to U direction. And so we're doing, so D minus P is this vector up here minus this projection. So we kind of go up, like we go up D, and then we go in the reverse direction for this P. And this vector here is W. Okay. All right. Okay. I know I presented that very straightforward, but when I actually figured this out, it was, I know my diagram might be kind of hard to see, but I hope you get the main idea. Okay. Now the whole point of this was to figure out geometrically what's going on, right? What is W geometrically with respect to V? The answer is, if we look at this diagram, and again, it's not a great, I know it's kind of hard to see, but if you draw out the diagram yourself, you will hopefully figure out that if you look at this triangle here, let me dot this. So yeah, so if you look at this triangle going on here, this big one, where this side is V and this side is W, so W is D minus P, and V is D plus P, right? So what W represents is the reflection of V over this line, which corresponds to D, right? Because the projection component is the projection, or I guess you could think of it like, the projection component is reversing, and then the decomposition component, which is perpendicular, is the same, right? So big idea, in 2 dimensions, P acting on V will flip it over will reflect it over the line perpendicular to the U line. Okay, all right. I know it's a lot, but it's what it is. So now we want to generalize, okay? So what happens in multiple dimensions? We have to be careful here. So we just have to kind of think about it. Now, if we imagine U is like an n-dimensional vector, right? It's an Rn. Then if we think about, so we can still write V equal to D plus P, kind of, okay? Same idea. So we can still think of V as a component which is along the U direction and a component which is not along the U direction, right? Perpendicular. But in n dimensions, if V is n-dimensional and P is just going to be like a component along a line, D is actually going to represent like the plane that's all of the components that are in the plane perpendicular to that line, right? So in 3 dimensions, D would be like represent like some vector in a plane that's normal to U. And so we still have in general, we still have like this same kind of idea in general, where you reflect this P part, but in n dimensions, you're gonna if I do P acting on V, then it's going to flip V or reflect V over the plane which is perpendicular to U, right? To W. That's what's going to happen in n dimensions. Okay, so I guess I should try and draw it out in 3. So if we imagine in 3 dimensions, like that? No, it's good. Okay. Imagine in 3 dimensions, we have some plane. I mean, honestly, like we can just think of the XY plane as this plane. So U is this k hat direction. And V is some vector V, like up here. Okay. Then if we apply P, we reflect V down, right, to W, which is below this plane, like that. Okay. So that's the geometric understanding of P. That's again, I know I hope I at least explained how you could get there, right? Like why it makes sense to think about the geometric interpretation of P. And once you start kind of playing around with it and you make this projection, like once you notice this projection thing, you draw out the diagram and everything, it kind of falls into place quite nicely. So even if I went maybe, even if you think maybe you would not be able to replicate that, it does kind of, when you draw out the picture of it and you work with it, it falls into place pretty nicely. Okay. All right. Now the other option, which is what I actually did, was I looked at the matrix P, right? And this was like the longer version. Okay, I know that was kind of long, but if you look at the matrix P, basically what you can figure out is that UU transpose is a matrix of rank 1. Okay. The reasoning is, I guess, if you think about, let's say U is 3-dimensional, then you could have something like, now I know this isn't unit, but not super important. But if you had, U was something like this, then because, like when you multiply matrices, you can do like the column vector, like you can, I don't know how to explain this in words, but you can kind of multiply like by the column vectors. So this is equal to 1 times this first column vector, which is just U, right? And then 2 times U and 3 times U. And so like all of the column vectors are linearly dependent, right? They're all just multiples of U. And so UU transpose is a matrix of rank 1. And then if you think of the range of this matrix, right? If I multiply this by any vector, okay, then I'm just going to get, again, a sum of multiples of U. So you can figure out that the range of this matrix is just basically vectors along the U direction, right? And then you kind of can realize that it's actually specifically the projection along the U direction. All right, cool. That's P. Now let's look at the big picture and let's try to solve this in general. So both important thing to note is that both P and Q preserve vector magnitudes, okay? Meaning it suffices to show that some unit vector will map onto itself, right? Because if we consider any other vector, if it maps onto itself, then so does the unit vector because matrices are linear, right? We only have to think about unit vectors. So if we consider only unit vectors, we want to think about how PQ will rotate and reflect the n-dimensional sphere centered on the origin, right? So if you think about only unit vectors, that produces the n-dimensional sphere on the origin. And we want to think about how PQ will transform that. And what we want to show is that in most cases, right, there will be a fixed point when we do that. Now, an important thing to also notice is that we can assume that U equals, so if we're in 3 dimensions, we can assume U equals K hat. And if in general, we can assume that U is equal to E sub n. So U is just the sort of new direction that's added in n dimensions. And the reason is because if you think about if U is any other direction, right, the math is all the same. You could just imagine rotating all of space, right? Or you could think about making a new coordinate axis with U in that direction, right? And that's a huge simplification. That's very nice because you can imagine it'd be really confusing if you had, U is off to the side, and then that means that the D plane is off to the side as well. It's just makes it even harder than it is. Okay. Now here's where Brouwer's fixed point theorem finally comes in, and I think you might have been able to see how it's relevant, right? Because we're trying to show that something has a fixed point, eigenvalue 1, or some function has a fixed point, eigenvalue of 1. Now the issue is that the unit n sphere is not convex, right? I mean, it's empty, okay? And we'd really like to use Brouwer's fixed point theorem here to solve this problem, but we can't because n sphere is not convex. So what we want to do is we want to find some kind of convex set which we can apply the theorem to. So one natural thing to think about is the unit n ball, okay? The unit n ball is convex. And so actually, if you think about the theorem, if we apply a function, a continuous function, PQ, to that ball, then there must be a fixed point within it. And so you would think, oh, there must be a fixed point, so then there must be an eigenvalue of 1, and that you'd be done. The issue is if that fixed point is the origin, right? That doesn't necessarily imply that there's an eigenvalue of 1. But if it's any other point and it maps to itself, then that means, that's an eigenvector and it has eigenvalue 1. But if it's the origin, it's not the case. And I looked into it and I couldn't actually figure out how you can resolve that. I'm sure there's a way to, but I didn't figure out how to resolve that. So once you ditch that idea, there's sort of a second choice you can think of, which is, granted, quite difficult, but I will try and draw it out. So I'll use 3 dimensions. And we're thinking about the just a sphere, right? Like what you normally think of as a sphere. Yeah, okay, that's actually all right. I'm not mad about that. So what we can also get this if we think about the equation. Oh my God, who is this? Anyway, if we also look at the equation of this sphere, right? So we have x squared plus y squared. And actually, I'm going to write x1 squared plus x2 squared because we're trying to think in general here. X3 squared equals 1. What we can notice is that every point on this sphere we can is determined by a point on this circle here. So every point on the sphere lies directly above a point on the circle or directly below. I guess you could kind of get that idea from, like, I think when you do integration, like if you want to find the volume of a sphere, for example, using integration, then who is this? If you want to use the volume, like prove the volume of a sphere using integration, then you kind of integrate over like the circle that I don't know what you call it, like the circle that's below it, right? So the point is that what you should realize is that this is a convex set, right? This is what we want, and for any point on this convex set on the circle, there's 2 corresponding points on the sphere, right? So if we imagine the function if we imagine like to think about PQ acting on the sphere, we can think about PQ just acting on this circle, right? So any point, let's say this point on the sphere maps to this point on the sphere, then we can think about just thinking about like this point on the circle mapping to this point on the circle, right? The point is that we know that there's at least one point on the circle which will map to itself, right? When we think in this way, okay? So there's some fixed point of the circle. Now that doesn't prove what we want completely, right? Because if some point on the circle maps to itself, that could tell us one of 2 things. The first is that some point on the sphere maps to itself, in which case we're done. We've proved the fixed point on the sphere. Or what could happen is this point, for example, on the sphere maps to the point directly opposite it, right? That's not very well drawn, but maps to the point directly opposite it. That does not prove that we have a fixed point on the sphere. But the point, that was terrible, but the point is that this actually doesn't matter. So we want to think about what case this happens. And our hunch is that, the condition was like, if 1 is not an eigenvalue of Q, then PQ has eigenvalue 1. We're hoping that this shows, in this case, Q must have eigenvalue 1, so we don't have to worry about this case, right? So if we think about it, we know that P, what is it? Oh yeah, we know that P acting on a point will just reflect it over this plane, right? So P acting on this point will map it here. So what that means is that Q does nothing, right? So if we did this, so like if we imagine this point here, Q must map it back to itself so it can reflect over there, right? If we did, man, I have a feeling this isn't somebody I know, but so if we do this kind of like the math way, like if we try to write this out mathematically, we have PQ acting on V equals, I guess, V prime, right? And so, like, because P and Q are orthogonal or whatever, they're invertible, right? Is that? Yeah, I think that means, yeah, they're invertible. So if we imagine sort of inverting P on this end, then the inverse, like if we invert the, I guess P is its own inverse. So if we invert P on this point, then we end up getting just, so we have P inverse V prime, which P inverse V prime is just PV prime, which is just V. Okay. So QV acting on V equals V. And Q has eigenvalue 1, which means we don't have to think about that case, and we're done. Okay, that's the whole solution. So, all right, I know that was a lot, okay, but like I said, this problem is really hard. This problem should have been B5, right? And this was actually, at least from my perspective, the most simple solution, okay? Because all the other solutions, sort of, they used a lot of algebra like a lot of algebraic manipulations, which didn't make a lot of sense to me. And this one kind of, like, you know, this geometric solution, I liked a lot. I liked a lot. Okay. Now, I will discuss, oh yeah, I'll discuss some main ideas to take away from this whole thing. So, one of my sorry, I just got a text from someone who sees that I'm streaming. But all right, let's think about big ideas here. Now, for the second part of the solution, which uses yo. Okay, I think more people wouldn't be joining on. So, so the second part of the solution, there's a few things that are really advantageous, like that we did, that make a lot of, that are sort of make sense. Okay, so this guy. All right. So the first is you want to try and simplify your input space without any damage. Okay, so what does that mean? Now, at first we were trying to think about what PQ does to all of space given any direction U, which is like, it's like too much to think about, right? Like that's really hard to think about. So what we did was we noted that we could assume U was just E sub n, right? And thank you. We could assume U was just E sub n, and we could just look at unit vectors, right? So we could just look at the n-dimensional sphere. So we simplified our input space that we're thinking about down to an n-dimensional sphere and one direction. And the reason this is advantageous, I mean, it's quite clear, makes it much easier to visualize and to think about. And we simplified our space without any damage to the actual problem. Like we didn't actually lose any generality, right? So this simplification will usually hinge on the properties of the function that you're considering, right? So we used the properties of PQ and sort of how rotations work in order to get those. So that's where you want to look. You want to think specifically what the properties of the function that you're thinking about. And in this case, actually, in general, due to the linearity of matrices, you only have to consider actions on the unit n sphere. You only have to consider unit vectors because because if you think about like a matrix acting on any vector, right? Then and it maps it to some other vector. Then if you think about the matrix acting on the unit vector, then it will map to just a proportional scaling of that image, right? It's just linearity of matrices, right? That's the big sort of property of matrices. Okay. So this is kind of seems obvious, but it's important to like actually ask yourself, So when we first looked at it, we wanted to apply Brouwer's fixed point theorem on the unit end sphere, but we couldn't because it wasn't convex, right? So in general, you want to ask if there's like a hole in your reasoning. You want to ask how can you patch that hole? Like how do you fix it? Yeah, it seems like an obvious question, but it actually forces you to pinpoint what's wrong and try to figure out how we get the right way, right? So what's wrong is that like the end sphere is convex, right? Or that it's not convex. And then how do we fix it? We need to think in terms of a convex set, right? Sort of gives you a little bit of direction in how you can figure out that you should consider the sort of like circle on the bottom. Okay. Now, I will go to now I'll go to some big ideas, some issues I have with this problem. Okay, and this applies in general. So first is, okay, don't jump the gun on an intermediate result. Okay, what does this mean? What does that mean? Oh, the glare is terrible, but so, and my handwriting is also not great. But what this means is, so if you're ever going through a hard problem and there's many steps to it and everything, like often when you find an intermediate result, or often when you like make some discovery or something like that, you get excited and like you kind of just like often when you find that, you get excited and then you speed through it, basically. I guess that means is okay, yeah. So once you get the result, once you get that like moment, you don't fully collect yourself and make sure that you know exactly what's going on before you move on. What that means is when you move on, you're disorganized and you're much less likely to make the right decision in the future, right? I guess that's a life lesson, okay? Just because you know something exciting happens, don't don't just like totally lose yourself, okay? Make sure you're fully collected and you're still moving in the right direction. I don't know. Okay, yeah. So actually, wait, let me look at, oh yeah. Okay, so relax. This is kind of going into what I just said. So you want to relax. Relax into breakthroughs. Okay, that's what I was saying. If you make some discovery, you need to relax into it. Okay, don't just like speed into it and then write down the result that you just got and like speed past it. Okay, because at all times you need to. Because the reason I'm saying this specifically, you need to be relaxed at all times when you're trying to solve something really hard. Okay, the reason I'm saying this specifically is because when you do make a discovery or breakthrough, you're going to be super excited and you're going to be all mentally jumbled and you're going to lose your relaxation. Okay. So when you make a discovery, relax into it. Okay, so as you kind of formalize it, don't rush, don't be hasty. Okay, relax out of breakthroughs. Same idea. So when you finally do get that intermediate result, or that discovery or whatever, yeah, when you finally do get that intermediate result, after you get that, you have to recollect yourself, and you need to be relaxed as you come out of that, right? Don't just get excited because you got halfway there, because then you won't be able to make it all the way there, right? Okay, and so third, so you want to both be aware of the big picture and your limitations. So when I was solving this problem, people are leaving, it's sad. That's all right though. When I was solving this problem, so of course, kind of at the beginning, we were thinking about the big picture. Like we want to show that PQ has some fixed point or something like that, right? So we were like aware of the big picture, and that's very important for your direction. But you also need to be aware of your limitations. What that means is, so when I was solving the problem, too often I would try to think of the big picture like too much, and I would try to like make a development on the big picture. But the problem was like I didn't know, for example, what P did. And so before I knew how P worked as a matrix, I was trying to prove the problem, like just totally, but that wouldn't work, because if P was just some random matrix, like you would not get at least, yeah, if P was just some matrix, you would not get this nice result, right? So you need to be aware of like can you actually use your current knowledge to solve the big picture, right? And the answer is, if the answer is no, don't try to, right? Okay, be careful. Okay, so be careful in generalization. Okay. Okay, so what that means is, all right. So when I was solving this problem, when I figured out like the whole idea of the D line and like or like the whole idea of how P works in 2 dimensions, you reflect over the line corresponding the D line, right? V to W. And so I very hastily generalized and assumed that in n-dimensional space, you would take a vector and you'd also reflect it over a line, right? Which is not the case. You actually reflect it over a plane. So the thing is, though, like in 2 dimensions, right? So you reflect it, in general, you reflect it over a plane, which has one less dimension than the space you're in. In 2 dimensions, that plane is just going to be a line then. But I was not careful when I generalized it. And so I made that mistake. And so I spent, maybe 30 minutes just kind of, with the wrong idea, the incorrect idea. So this kind of goes into like the whole relaxing into and out of breakthroughs. So you need to be careful, like when you sort of think you have the answer, right? Or like at least when something works for a small case, you often think that you have the answer for the general case, or you're excited, and so you generalize very, very quickly, and oftentimes you can be wrong, especially if the problem is hard. So just always be wary that you're not generalizing like too hastily. Okay. And lastly, for a mental change. Now this is, I'm going to use an example to demonstrate my point. So let's say you're given x squared minus y squared equals 20 and x plus y equals 5. And you want to find x minus y. Okay. All right. Pretty basic problem. But so like hopefully you can notice, for example, that x squared minus y squared is x minus y times x plus y, right? So if x plus y is 5, then x minus y is 4, right? Very direct solution. Now, the reason I bring up this example is because the common misconception or mistake that people will make if they haven't seen something like this is that they assume that they must know x and y in order to solve x minus y, right? But that's not the case. You just need x minus y. You don't need them specifically. Now, it seems obvious, but this can happen much more subtly, or you can make this sort of misconception much more subtly on a difficult problem. So for example, when I was solving the problem, I assumed that I need to know what the matrix P looked like and what it was doing, right? I assumed I need to know what the matrix P looked like, but really I needed to know how the matrix P acted, like on some vector V, right? So I wanted to know PV. I assumed that I needed to know P, but that's not the case, because if you actually write out PV, you get a very nice, the whole idea of like the projection comes out very cleanly. But if you just think about the matrix P, that doesn't come out as cleanly. So make sure that like you really ask yourself, like, what is it that I actually want to know? What does it actually need to know? And make sure that you're not making the misconception that you need to know something else, right? Okay. All right. Whew. So let's wrap up. Now, this was, like I said, a very hard problem, but after I spent so much time on it, I felt like I needed to deeply understand the solutions to the problem. So the point is that, even though this problem is probably out of my league, I guess. Okay. Granted, I did make some good progress on it, but it took me a long time. I would never be able to solve something like this on the exam. Despite that, you can often milk a lot more out of problems than you think, right? And so, sort of any hard problem that pushes you and challenges you is like a huge learning opportunity. Even if the thing that you learn is that you shouldn't do problems that are that hard, that's still a great thing to know, right? That's gonna save you a lot of time to be more effective and everything. So you can always learn something. Like if something went wrong, if something was hard, then there's something to fix, right? Okay, so I will try and do these more frequently, but I'm not gonna say specifically a schedule for it yet because I don't exactly know. It's kind of just comes as I review these problems and do them and everything. And it takes a lot of time, obviously, because they're quite difficult. But in general, I will post I guess on my YouTube channel. I don't know, they have a post thing. Again, I'm not sure, I would like it if you subscribed or something like that, but I don't care. I don't care that much. But you should if you want to get notified if I'm going to do something like this, because I will post on the channel instead of just in the math team group, because I don't want to flood that group. Okay. All right. So I hope that was useful. Just smash like and subscribe, and I will hopefully see you in a couple weeks.